Alright, your standard disclaimer that staying in this meeting means you consent to being recorded. So yeah, just so you know. Alright, so welcome everybody to our 12th week of Tyee Science Club, of course using the tryouts as week 1. Today we'll be talking about chemical reactions and going into some basics of equilibrium. So let's see what we're talking about today. So first of all, let's talk about the different types of reactions that we have. The main ones we're going to talk about today are the precipitation reactions, reduction oxidation, also known as redox reactions, acid-base, as well as dissociation reactions. Sometimes some of the lower level chemistry likes to throw a bunch of somewhat useless ones in there. Single replacement is essentially a type of reduction oxidation, so we'll talk under here. We just covered everything under here. Combustion is also another type of reduction oxidation. It's exothermic, so they gave it a different name, but it's all just under redox. Next thing is synthesis, which is basically a couple different compounds forming one. It's not really too special. And decomposition is one thing becoming a couple of things. So these aren't very special, and we won't talk too much in depth about them. The main ones are precipitation, redox, acid-base, and dissociation. Some of you may have heard of the double replacement or / double displacement reaction. We're going to cover that under precipitation today. Alright, so let's get started first with precipitation reactions. Alright, so precipitation reactions involve a reaction between two ionic compounds. So these reactions occur when two soluble compounds are dissolved together in a solution. Alright, so two of the dissociated ions, dissociation, which we'll talk about later on today, will come together to form a solid, and this occurs when the two molecules bump into each other and then they react. This solid is not soluble, meaning it can't dissociate in water, so then it precipitates out of the water as essentially a precipitate, and you can see changes the color, makes it cloudy, makes it yellow, a number of things. So a very famous model reaction of this is silver nitrate plus sodium chloride goes to sodium chloride plus sodium nitrate. Now we notice sodium chloride, if you don't know yet, is just table salt, NaCl, while silver nitrate is a pretty common compound that you can buy. Now this, notice later on we'll talk about solubility rules, but in general, compounds that include a nitrate are generally soluble, as well as compounds containing a group 1 ion or an alkali metal ion are also generally soluble. So in this case, you notice AgNO3 is soluble and NaCl is soluble. However, when they react, when the AgNO3 dissociates into Ag plus and NO3 minus, and that one of the Ag plus hits one of the Cl minus from NaCl, this is no longer soluble, and they form a solid in the liquid, and it makes the liquid turn white, because in this case AgCl is white. However, NaNO3 still stays aqueous, meaning dissociated. Now, here's a quick demonstration of this reaction in play actually. So you notice right here, he has his solution of, I believe this is currently sodium, sorry, not sodium. This should be the silver nitrate solution. Now he has a beaker of, a graduated cylinder of sodium chloride, aqueous sodium chloride that he's going to add into here, and you guys can see what happens.
Alright, so here's the...
Well, I'm not sure if you can hear the audio, but that was just a bunch of people wowing. And just curious, can you guys hear this? Because we have a video later on.
Oh, I could hear it.
Alright, sounds good. Okay.
I only see a cup.
Yeah.
There's nothing.
Right now it should just be a cup, right? So you notice he has a beaker here, right? Initially, initially it was full of a clear liquid, but then it turned cloudy and white. So you notice the clear liquid.
All right. So here's the
with the other solution, it starts forming a white powderish thing, and that's essentially the solid state sodium chloride. Let's go to the next slide. Okay, the next slide, we'll talk about the net ionic equation. So many of you probably have heard of what a chemical equation is, which is essentially this thing that we talked about earlier. However, this does not accurately represent what we actually see in the solution if we go to the molecular level. If we actually go to the molecular level, like I mentioned earlier, the AgNO3 splits apart into two ions because it's aqueous and dissolves in water. Similarly for NaCl, it splits into Na plus and Cl minus, and that's represented right here, where we split it apart and added plus signs in between. On this side, because AgCl does not split apart, it remains as one thing, while the NaNO3 does split apart, so we represent it as two parts here. We can just term this as an ionic equation. It's not net ionic because of a couple of things. Notice that you have NO3 minus on this side, as well as NO3 minus on this side, and you also have a duplicated Na plus. Similarly to in math equations, you can essentially just get rid of this NO3 minus and Na plus because they're something called spectator ions, meaning they don't actually participate in the reaction at hand. Therefore, if we cross them out, we finally end up with Ag plus Cl minus goes to AgCl, and this is called the net ionic equation. So usually when they ask you to find the net ionic equation of a complete chemical reaction, what you want to do is split the aqueous compounds into ions based on what ions are present, and then cancel on the left and right side. Usually, if you want to, you can simplify the process by just directly going to the solid particle and then splitting that onto the left side. Alright, next is the redox reaction. So before we go to redox, let's actually revisit this real quick. The important part to note here is that all of the ions in this scenario retain the same charge. So notice that Ag plus, even in AgCl, still retains its plus charge. Na plus never changes its charge, as does NO3 minus, and Cl minus starts as -1, and then in this compound, technically we can consider it to be -1 as well. So no electrons are being transferred between atoms, and this is extremely critical. AgCl is still an ionic compound, so they're still not sharing their electrons as a covalent bond. Alright, so next we're talking about redox reactions, and these differ from other types of reactions because electrons are transferred in this reaction. So some atoms will gain electrons and others will lose electrons.
Are you on the redox equation? I see the net ionic equation.
Oh, you might have a little bit of lag right now. I switched relatively recently. Right now I'm on the slide that's titled Reduction and Oxidation. Alright, so redox, like I mentioned just now, redox reactions concern the transfer of electrons. There's a term we call the oxidation state, which essentially tells you what charge essentially there is on a particle. Now this is a little bit of a simplification, but you can essentially see it as such. When a redox reaction occurs, certain compounds in the reaction will experience a change in their oxidation state. And this is why it's called a redox reaction, because sometimes it's reduced and sometimes it's oxidated. Compounds are. And we'll go a little bit more into that in the next few slides. Remember, this category also includes combustion, as combustion is just a form of reduction-oxidation reaction that's a little bit special because it gives off a large amount of heat. Alright, well, we have a crash course video. I recognize that there may be some... Alright, so if you can't view the video, please go ahead and click on the link in Room X and view it on your own. Otherwise, I'll also be streaming it here. So here we go. It's about
the electron is to chemistry what money is to capitalism. It's all about who has it, who wants it, what they're willing to do to get it. Electrons are what make it possible for an atom to bond with other atoms to form molecules, and when that happens, a tremendous amount of energy can be exchanged in the process. But not all chemical reactions involve electrons changing hands. Acid-base reactions, you'll recall, are more about swapping protons. But because electrons are the real coin of the realm in chemistry, the most important reactions that take place on Earth involve the transfer of one or more electrons from one atom to another. These are redox reactions. Redox, which is a portmanteau of reduction oxidation. But what's up with those words? You know what reduction is, making less of something, and then oxidation maybe has something to do with oxygen, well, sometimes, but not always. These are actually super terrible choices for what is actually happening in redox reactions, but we are stuck with them. Reduction is when a substance gains electrons. Yes, it gains, which is the opposite of what the word reduce means. Fantastic. And yes, sometimes I want to punish the people who named these things so inaccurately, but they didn't know any better and they're all dead, so we can't do anything about it. Proto-chemists would make pure metals by heating or smelting their ores. And they noticed, during the smelting, that these substances would become lighter, so I guess it's not crazy that they decided to say that these substances were being reduced. Our old French friend Antoine Lavoisier figured out that this was because oxygen gas was actually leaving the compound, making it lighter. What he didn't know was the actual chemistry involved. Oxygen is, unsurprisingly, the quintessential oxidizer. It pulls electrons off of one molecule to make itself more stable. But if you heat it up enough, it gets all energetic. Today, we understand that oxidation and reduction are all about electron transfer. So you might think that we'd rename them, and some chemists have tried producing terms like electronation and de-electronation. But once a set of terms is decided upon and used for a while, it's pretty difficult to uncreate it. So we're stuck. To keep these seemingly nonsensical names straight, I rely on the phrase oil rig. Oxidation is loss of electrons, reduction is gain of electrons. We just gotta know this stuff, because it's everywhere. When your cells convert sugar into energy so you can move and breathe and think, that's redox. When plants photosynthesize sunlight into food, that's redox. The battery powering your laptop? Redox. Fire? Also redox. Since electron swapping is the name of the game here, when you study redox reactions, it's important, critical, absolutely essential to keep track of the electrons. Think of them as dollars or pesos or pounds or euros. In any transaction, one person is going to gain them and the other is going to lose them. And to stay on top of things, you have to keep tabs on who's ahead and who's behind. Atoms are fond of sharing electrons, though, forming covalent bonds, so sometimes keeping track of where they are and where they're going to end up isn't quite so simple. Let's think of every covalent compound like a marriage, though it's going to be a weird marriage, because there might be 6 people in it, sometimes the same person several times, without commitment, no commitment, and also no emotions. Don't think too much about it. Like in a marriage where money gets shared, covalent compounds share electrons. The trick is figuring out who gets the cash when the vows break. So we've created a useful little system assigning electrons 100% to atoms that are actually at the moment sharing them. The number that we assign is the atom's oxidation state, or oxidation number. Even though we are of course aware of covalent bonds and the sharing of electrons, the processes are easier to follow if we imagine that the atoms are already splitting up the bank account, as if they were in an ionic or non-sharing bond. So an atom's oxidation number is basically what its charge would be if it actually owned all of its electrons exclusively, like the newly minted bachelors that they may become. So to figure out those oxidation states, or oxidation numbers, we have some simple rules for some atoms. First, the oxidation number for any element by itself, whether it's monatomic or diatomic or polyatomic, like an atom of calcium, or a molecule of H2, or an even bigger molecule of sulfur S8, the oxidation number is 0. Atoms, by definition, do not have a charge. If they had a charge, they would be ions, and if they're sharing with themselves, they share equally. Second, for a monatomic ion, basically a charged atom, it's simply the size or number of its charge. So the iron 2 in Fe2+ has an oxidation state of +2, while a chloride ion is -1. Third, oxygen, which is unsurprisingly all over redox chemistry, almost always has an oxidation of -2, unless it happens to be in a peroxide molecule like hydrogen peroxide. Fourth, hydrogen is +1, and fifth, fluorine is -1, as are all the other halogens most of the time. Pretty much unless they're bonded to fluorine or oxygen, because fluorine and oxygen are so bad that they can make anybody's oxidation number positive, if you know what I mean. And those are the rules. That's all you need to know. Now, The total of all the oxidation numbers of all the atoms in a neutral compound will add up to 0. Like water with 1 oxygen with a -2 oxidation state and 2 hydrogens at +1, and voila! The neutral compound has an oxidation number of 0. A polyatomic ion, on the other hand, has to work out to have an oxidation state that matches its charge. So SO42-, the sulfate ion, has 4 oxygens for a total of -8, but we don't have a rule for sulfur, so I guess we just give up and walk away. Who cares anymore? No! We use like 3rd grade algebra because we have to end up with an oxidation number of -2 for the whole compound. We know that sulfur, in this particular compound, has an oxidation state of +6. But sulfur's oxidation state isn't always +6, and that's why we don't have a rule for sulfur, or a lot of other elements for that matter, because oxidation states of most elements change depending on what they're bonded with. Now we can use this same logic to figure out what happens when these compounds interact in redox reactions. Molecular divorce courts of electrons changing hands, being haggled over and traded, with some players taking big profits while others lose nearly everything. Them's the breaks. Let's start out with a simple example. A chemical reaction that I believe has saved more lives than any other in the history of chemistry, created by a war criminal to blow people up during World War I, the Haber process. The Haber process removes the ultra-stable elemental nitrogen from the air and combines it with hydrogen to form NH3, ammonia, for use in bombs and also in fertilizer, increasing the carrying capacity of the Earth by billions. Nitrogen in the air exists as elemental diatomic nitrogen, and hydrogen likewise is also diatomic H2. So we know that starting out, all of the atoms have an oxidation state of 0. The product of the reaction, ammonia, is a neutral compound with 1 nitrogen and 3 hydrogens. The hydrogens each have an oxidation state of +1, remember the rules, so nitrogen must have an oxidation state of -3. Now, the electron to chemistry what money is to capitalism. It's electron, the oxidation state went up. What oxidation states are doing? It's a neutral compound with...
Alright, so I meant to stop you here, just to note, notice here that the oxidation states are changing, right? Let's see, I think he labels them in a moment. Yeah, here we are. So originally the nitrogen started out as 0, and hydrogen was also 0. But then when hydrogen went into a compound with nitrogen to form ammonia, like he talked about earlier, H likes to be in +1, so it's +1 in this case. In order to balance out to get a balanced charge, you get the nitrogen must be -3. So notice here that each atom of nitrogen gains 3 electrons in this case, and each atom of hydrogen loses 1 electron. Now let's count how many total electrons are exchanged. Notice here that each nitrogen gains 3, and because there are 2 nitrogens involved, that's 6 total gained by nitrogen. However, there are 6 hydrogens and each loses 1, so there are 6 electrons lost. Therefore, overall, the total amount of hydrogen and electrons gained and lost is 0. This follows from conservation of charge, which is an important part in physics. You can't create or destroy it. Let's continue.
Gained electrons, its oxidation state went down, and so it was reduced. So at least when talking about what oxidation states are doing, the word reduced makes sense. Hydrogen lost electrons, the oxidation state went up, and it was oxidized. Now this is a pretty simple equation to balance, but redox equations can be a huge headache sometimes because of the number of individual atoms involved. So we often have to balance them in half reactions. So even though we don't really need to do the half reactions because this is a pretty simple equation, we're going to do them anyway, just because it's an example that's simple to start with. So start out with the nitrogen getting reduced. We have N2 with an oxidation state of 0 becoming NH3 with an oxidation state of -3. First, we balance the number of nitrogens, then add the number of electrons that we need to have there be the same number of electrons on each side. Do the same with the oxidation half of the reaction, and then combine them to get your whole reaction with the electrons canceling out. Now yes, maybe that seemed like an unnecessary step, but allow me to show you a more complicated example that will prove how necessary it may be. In this flask is silver diamine. We're going to use some redox chemistry to get the elemental silver out of it nice and clean and shiny, and it's not gonna be no simple Haber process. The silver diamine is going to react with an organic aldehyde, any aldehyde actually. The business end of the aldehyde is the CHO end. The R in organic chemistry is a symbol for...
Notice here that this part is more for fun. You don't actually need to know this because it's a little bit more advanced.
organic group of atoms, and in this reaction, those atoms don't matter. The silver diamine reacts with the aldehyde and hydroxide, creating carboxylic acid, ammonia, and water. First, let's assign ourselves some oxidation states. The silver is in a complex with two neutral ammonias that are going...
Alright, I'm actually, in fact, going to skip this because it's not very relevant, and you can go ahead and check this out. It's a pretty interesting reaction that occurs in organic chemistry, and if you here's start again. Alright, so let's continue on with the rest. If you're still watching the video on your own computer, please now leave it, and then we'll continue with the rest of our PowerPoint. Alright, so I hope that was, oh, sorry, start this again. Alright, so important part to remember here about this is not all the nitty-gritty details. The main thing to remember that we need to know is which is which. So he mentioned using oil rig, which is a very popular term that you'll hear about later as well. It's essentially a mnemonic where OIL and RIG stand for oxidation is loss and reduction is gain. So this is one thing that I like to use. Remember that it's a loss of electrons and gain of electrons. I find it very helpful. Alternatively, I also, when I'm not too sure of myself because these get mixed up pretty easily, I think of reduction as a reduction in charge. So when something is getting reduced, its charge is also getting reduced. So that's how I assign it. There's also a term called reducing and oxidizing agents that I think you guys should know. These are essentially compounds that will give off and take electrons from other compounds. A reducing agent is called a reducing agent because it will go ahead and reduce the other compounds, while oxidizing agents will instead oxidize other compounds. Alright, so remember how Hank, I think this is Hank, the Green Man. Remember how the Green Man mentioned that oxygen and oxidizing are related, but not always? That's because oxygen is actually a very, very strong oxidizing agent. It appears in very many compounds, and as it takes a -2 charge, the rest of the compounds around it itself is reduced from 0 to -2, 2 minus, sorry, -2, sorry, is correct. It is reduced from 0 to 2 minus, and therefore it oxidizes other agents. And because the main idea is because oxygen is so electronegative, I think the only element more electronegative than oxygen is fluorine. It essentially attracts a lot of the electrons from other elements and molecules, that the other elements and molecules get oxidized while it itself gets reduced. Alright, now on to our third type of reaction, which is the dissociation reaction. This is essentially what occurs when an ionic compound dissolves in water. Alright, so like I just mentioned, it's the splitting of an ionic compound. And we must note that although a large number of ionic compounds are soluble, not all of them are soluble. Or technically, we can plot solubility on a spectrum, meaning there are compounds that are very soluble and compounds that are not very soluble, but there's no real compound that's not at all soluble or always soluble. But in large proportions, we can make some assumptions. So dissociation of an ionic compound is essentially a chemical reaction because it goes from a solid state NaCl to aqueous state or dissociated state of NaCl. So this is our reaction here. NaCl goes to Na plus Cl minus. Next, we'll introduce a term called the equilibrium constant, K sub Eq. And this essentially describes the equilibrium state of a reaction. So in general, the K sub Eq is equivalent to the product of all product concentrations over the product of all reactant concentrations. Now this is a little bit more advanced, so it's okay if you don't follow too much. In this case, in many cases, we'll have different. We'll replace this EQ with a specific situation, and in this case, because we're talking about solubility, we'll replace the EQ with an S. So K sub S is essentially the variable for solubility, equilibrium solubility constant. Alright, so in this case, can somebody tell me, oh, well, I already put this up here. I meant to animate it, but this is what the equation for the constant of solubility looks like for this reaction here. Notice that our two products are Na plus and Cl minus. So what we must multiply them and put them on the top. Notice that the square brackets are here. The square brackets indicate that we're looking for the concentration of this ion in moles per liter. In addition, the reactants in this equation is NaCl only, so we're only putting NaCl on the bottom. Now I have a quick question for you guys. So I'll tell you right now that, well, you guys probably know, table salt is very soluble in water. So would you guess that the K sub S would be a very high value, a value about 1, or a very low value close to 0? What do you guys think?
A high value.
A high value, right? Because what happens here is if we dump a bunch of table salt into water, almost all of the NaCl will be gone. Because when you look at a molecular level, it will have turned into Na plus and Cl minus. So this will be a positive, pretty large number, and this will as well. While this will be a very small number close to 0. That means when the denominator is extremely small, we know that we'll get a very large value. And I'm not exactly sure what the value is, but I think it's something along the lines of 1 billion or more. So basically, if you look at the molecular level, 99.99999% will be dissolved. And in this case, at our level, we can just assume all of it dissolves. However, magnesium chloride is, magnesium chloride is also a different compound that will dissolve. Now, the interesting to note here is that when we had NaCl, Na is sodium is an alkali metal, meaning it's when it's in its ion form, it has a 1 plus one charge. Whereas Mg will have a 2 plus charge, which is different from before. Now we notice that our original compound was MgCl2, and this splits into Mg plus Cl plus Cl, essentially. Although we can sometimes write this as Mg plus 2Cl, in reality it's splitting into 3 different ions, which is why when you find the top part, you actually have to square the Cl part, because you're essentially taking Mg2 plus times Cl minus again, because you can treat the two chlorines as separate. This introduces the fact that we didn't touch on here. When your product or reactants has a certain element with a coefficient in front of it, you have to put that coefficient as an exponent. In this case, we had 2Cl minus, so we're putting the 2 as an exponent here. So that's something to remember. Alright, so there are a couple solubility rules that you guys should remember. In fact, most of this is a very big table that I left here for reference, but I'll highlight a couple that I think that are especially important. First of all, group 1A ions are soluble, meaning all alkali metals, well, not all, but the vast majority of alkali metals are soluble. In this case, you can essentially assume all of them do. That means anything with Na plus or a similar compound in it will automatically be soluble, and you don't really need to worry about it anymore. In addition, nitrates and acetates are soluble. Perchlorates don't really come up that much, so you don't really need to worry about that. But nitrates and acetates are the ones you have to remember. NO3, anything with NO3 is soluble. I also mentioned this earlier. Next, the number 3 is something you might want to remember, but it's not too important. Usually, halogens are soluble, except when paired with silver, lead, copper, or mercury in its 2 plus oxidation state. Okay, and notice that we found that AgCl2. Oh, sorry about that. We found that AgCl2, AgCl was not soluble earlier when we showed the video. In addition, everything else you can essentially ignore. Hydroxides are in general hydroxides, or compounds with an OH minus, are not soluble except for the strong bases, which we'll talk about next. Alright, so our last category that we're going to talk about today are the acid-base reactions. Alright, okay. Give me a moment, sorry.
just one question.
Go ahead.
Isn't Cl chlorine in gas form poisonous?
Yeah.
So when you dissolve it in water, why doesn't the water become poisonous?
Alright, that's a very good point. So, like you mentioned, chlorine gas is a poisonous yellow gas. And notice here that, however, it's in Cl minus form. And chlorine gas, when it exists in the atmosphere, well, not in the atmosphere, but in gaseous form, forms a Cl2, meaning it's a diatomic gas. So Cl minus won't actually form a Cl2 unless there are some outside factors going on with it. Cl actually, because Cl is a halogen and it's a third most electronegative element, I think actually. It prefers to stay in the Cl minus state because it is more stable. It should be more stable than the Cl2. And when there's water there to help stabilize it, because water's polarity, it prefers to stay as Cl minus. Otherwise, we would all die when we drank salt water because it contains a lot of Cl chlorine ions. So in general, in water, Cl minus is a more stable state, so it doesn't actually go and form the chlorine gas.
Okay, thank you.
Alright, no problem. That was a great question. It's very interesting. Alright, then the last topic we're going to talk about today is the acid-base reaction. As you can guess, acid-base reactions concern an acid and a base. But what exactly are an acid and base? In order to find out, we must go through acid-base theory. So there are three main types of theory: Arrhenius theory, Bronsted-Lowry theory, and Lewis theory. We'll talk about all of these today, and this is approximately also the order that they were proposed, and this has somewhat of an effect. We'll also touch on what pH is. Some of you may know pH is essentially equal to the negative logarithm of the concentration of H+ ions, meaning if you have a low pH, you'll have a lot of H+ ions in the water. And we'll talk about this a little bit later when we talk about strong acids. Another thing you should know is something called autoionization. Autoionization means that when water collides with water, sometimes, if you have like a pure solution of water and two water molecules collide, sometimes they'll form a hydronium atom, which is H3O+, as well as an OH-. And this is important in the later slides. So the first type of theory that we'll talk about today is the Arrhenius theory.
See any slides?
Can you say that again?
I don't see any slides.
Maybe try leaving the stream and then rejoining. Can anybody else see it?
It's there now.
Alright, thank you. So Arrhenius acids are probably the ones you guys are most familiar with. And it states that acids and bases dissociate in water and form H+ and OH- ions respectively, meaning acids will form H+ and bases will form OH-. So very common examples are all the household acids that we think about. HCl, hydrochloric acid, very famous for being rather corrosive. Sulfuric acid, which is also very corrosive. Sodium hydroxide, which will dissociate and dissolve in water, unlike other hydroxides, as well as calcium hydroxide and a number of other acids and bases that I'll show an image of it later on. There's also a special case of NH3. What happens here is that normally HCl, notice that it has an H in it, and it breaks apart into a H+ and a Cl- ion. And H+ essentially is what creates the acid. However, NH3 is special. NH3 is actually a base, even though it has an H in it. Notice all the other bases, such as NaOH and CaOH2, have all of them have an OH in it, and this OH comes off to form the base. However, ammonia is a base that's a special case because instead of taking an OH from itself and then putting it in the water, it takes an H from the water and leaves an OH in the water. So essentially what happens is the NH3 reacts with an H2O to form NH4+ and OH-, and this causes it to essentially be in a base. So this is a very curious one. So our next type of theory is the Bronsted-Lowry theory, which is basically a repeat of this, except generalized to not just water, but also other solids and other things. For example, citric acid typically comes in solid form. Okay, so basically what Bronsted-Lowry theory says is that acids are proton donors while bases are proton acceptors. So you guys might think, we were talking about H plus ions earlier, but now we're talking about protons. What's the relationship? Well, remember that a hydrogen atom is basically just a nucleus with one proton and an electron. So when you have an H plus ion, that essentially means it's only left with a proton. So when you're exchanging H plus ions, we can actually call it straight as a proton, because that's essentially what you're exchanging. So a lot of times in chemistry, you'll note that H plus and proton are often inter-exchanged. One example of this is when you learn about HNMR spectrums, or hydrogen nuclear magnetic resonance spectrums later on. Sometimes they'll just call it proton NMR instead of HNMR. So it's just a name difference. Alright, so what Bronsted-Lowry theory does, like I mentioned earlier, is that it expands the field of acids. Lewis theory does this even further. Lewis theory states that acids accept electrons and bases donate electrons. So notice here that acids were originally donors and bases acceptors, but now this is flipped when we switch to electrons. Now, Lewis theory is quite more advanced, but the most important part is to remember that acids accept electrons and bases donate. This is something that might very likely be quizzed in Science Bowl. This expands it to even further and kind of overlaps it with some redox reactions, and allows us to label some special acids, special compounds as acids. One example where Lewis theory is especially prominent is when carbon dioxide is dissolved in water. So notice that when we just have carbon dioxide and water, neither of them seem to be an acid, right? But when carbon dioxide dissolves in water, they form carbonic acid, which is H2CO3. This is a very curious thing that is explained by Lewis theory and will appear on your extension for this week. Alright, finally, we're getting close to the end. We'll talk about weak and strong acids. So essentially, the difference between a weak and a strong acid is how much it dissociates. So notice that we have Ka and Kb here. Remember how we talked about Ks and Keq earlier? This is essentially just the constant of equilibrium for acids, hence the A, and bases, hence the B. Additionally, if we take the negative logarithm, similar to pH, we get pKa and pKb. And the more acid dissociates, the stronger it is. For example, HCl almost completely dissociates into its member ions, while something like, acetic acid, or the acid you'll find in vinegar, doesn't completely dissociate, and in fact doesn't dissociate much at all. But it does dissociate some, so you can still count it as an acid, as well as getting that sour taste that is very prevalent. Alright, here's a list. I just go through it really quick. If you want to come back and review it, that'd be great. So strong acids: hydrochloric, hydrobromic, hydroiodic. Notice that these all start with hydro. So these are collectively named the hydrohalide acids. Notice that HF is actually a weak acid, hydrogen fluoride. Nitric acid, HNO3, sulfuric acid, H2SO4, and perchloric acid, HClO4. So ClO4 is a perchlorate ion. Commonly also included on this list, which has been omitted in this image, is chloric acid, which is HClO3. So you can just think of it as taking off a 4 and replacing it with a 3. Strong bases, on the other hand, are much easier to remember. Not all of them are included on this list because there are quite a few more strong bases. But remember how we talked about alkali metals earlier on? All alkali metals plus OH form strong bases, and all alkaline earth except for beryllium, which is the first one, combined with OH will form a strong base. So that's pretty easy to remember, if you look at a periodic table at least. Alright, and finally, there's a lot of different interactions between acids and bases, but we'll talk about strong acid and strong base equilibrium today. There's also weak acid, weak base, and as well as weak acid, strong base, and vice versa, which are rather interesting. So remember from our discussion on this slide that HCl and NaOH are strong acids and strong bases. These are actually very common and will often be used for demonstrations. So a common experiment not very common actually, and it's not what's recommended at home whatsoever, is that a chemistry teacher will have some HCl and some NaOH, and both of these can be extremely harmful when drank. And they'll mix them together and get H2O and NaCl, which they'll subsequently drink. Now this is actually very harmful and could go very wrong, but it utilizes the idea that HCl and NaOH split apart to form H plus, Cl minus, Na plus, OH minus, and the H plus and the OH minus combine to form H2O, and the Na and Cl remain as dissociated ions, and thus it's no longer very harmful. So what happens here is that they reach equilibrium, meaning when all of the H that's come off the HCl has reacted with all of the OH that come off the sodium hydroxide. Now this is usually a pretty fast reaction. Alright, our very last topic for today is conjugation, and this will appear on your extension as well. So conjugation is essentially what happens when you remove a proton from a proton or H plus from a hydrogen, or add a proton or H plus to a base. Now this is what's called conjugate base pairs, and essentially, well, this will be investigated more, but the stronger an acid is, the weaker its base, and the stronger a base is, the weaker its acid. And this will be explored further in the extension. And this slide is there for reference, and we'll ask you to investigate it more in the extension, like I mentioned. Now, some extras. Credits to slides go for the template. Pictures are licensed under Creative Commons and from Google. And if you would like to learn some more about Bronsted-Lowry theory as well as Arrhenius acid theory, click on this link, as well as Lewis theory on the source from Purdue. So thank you everybody for listening to our presentation.